Welcome back to The Explainer, everyone. I am absolutely thrilled to have you here today. For all you focused learners out there, we are essentially putting on our digital detective hats for this one. We are going to conduct a forensic autopsy on a catastrophic architectural failure that is happening right beneath the screens we stare at all day long. But more importantly, we're going to look at exactly how we can fix it. Okay, let's dive straight into this. Take a look at this chilling quote directly from our sources. It warns that Google is a snake eating its own tail, and it describes our entire modern computing pipeline as, quite literally, tricking rocks into thinking using lightning. I mean, that instantly establishes the massive macro-level stakes of our investigation today, right? We are looking at a built-in hardware paradox, where our current digital architecture is mathematically destined to just consume its own data supply. 80 to 90%. Think about that for a second. That staggering number represents the estimated percentage of modern AI compute cycles that are relying purely on hidden, microscopic hardware approximations rather than exact math. So when these massive language models do their heavy lifting, they fundamentally just guess the nearest mathematical truth. To understand how we can actually solve this crisis, here is a quick roadmap for today's explainer. We're going to start with 1, the FPU gambler illusion, move to 2, the wood chipper effect, and 3, hitting the trig wall. After that, we'll look at the actual fix, 4, riding the tortoise, 5, enter the ALU surveyor, and finally 6, absolute digital truth. Let's just jump right in. Section 1, the FPU gambler illusion. To truly grasp what is going wrong with modern computing, we have to look at this massive physical clash happening right on the silicon of your computer's brain. On one side of the chip, we have the floating point unit, or what the sources refer to as the FPU gambler. Now, it's wildly fast for sure, but it's probabilistic and it's lossy. When it hits heavy math, it relies on completely secret proprietary seed tables burned right into the silicon. It essentially throws darts at a board to guess the answer. Now, contrast that with the arithmetic logic unit, the ALU surveyor. The ALU might be slightly slower initially, but it deals strictly in absolute exact hardware truth. It acts like a surveyor out in the field with a precision laser. It executes on a perfect metronome of clocked voltage, where 1 + 1 = exactly 2, globally every single time. So what happens when we build our most advanced AI on the back of that guessing gambler instead of the precise surveyor? Well, that brings us to Section 2, the wood chipper effect. Our sources use this brilliant and honestly kind of terrifying metaphor. Think of the FPU like a giant digital blender. Step 1, the AI ingests exact source data, so maybe a copy-graded book or critical financial records. Step 2, the FPU approximates the heavy math of that data using those secret seed tables, basically arbitrarily chopping off tiny decimals. Step 3, because that math was a guess and not a precise trackable calculation, the original mathematical provenance is permanently destroyed. You know exactly what went into the blender, sure, but you absolutely cannot reverse engineer a smoothie back into the exact fruits it came from. The history is just gone. Section 3, hitting the trig wall. You see, this guessing game isn't just some minor glitch you can ignore. It creates a fundamental physical barrier. Traditional AI architecture relies heavily on continuous geometry, so think of complex Euclidean curves like sine and cosine to map vectors. But our computers are discrete, rigid, binary machines. When you force continuous curves onto a discrete grid, you create a massive trig wall that literally forces the processor to guess. It chops continuous numbers into arbitrary tokens, creating a digital Zeno's paradox, where the hardware tries to infinitely approximate the curve but never actually reaches it. And this inevitable gap? It leads directly to non-deterministic drift, associative bleed, and all those infamous AI hallucinations we keep hearing about. Now, how do we fix it? Section 4, riding the tortoise. Now, what's really interesting about this slide is how researchers are actually fixing this by reaching back into ancient math. The elegant solution to this crisis is what the sources call Pell-Smith rational coordinates. Instead of trying to draw smooth, continuous circles that constantly force computers to guess, the Pell-Smith solution replaces continuous trigonometric angles entirely with exact, division-free integer mathematics. It maps circular geometry onto a strict rational coordinate ring. By doing this, it completely bypasses Shannon's rate distortion entirely. It literally never lets the hardware make a single guess. Okay, let's break down the mechanics here. First, it utilizes Pell's equation, which is a strict mathematical rule demanding pure, exact whole numbers, no decimals allowed. It then leverages Chebyshev polynomials as a translation layer, which turns messy infinite trigonometry directly into division-free integer algebra. But the real engine here, the secret sauce, is the use of Pell-Lucas sequences, specifically mapping ratios of an-1 over an. Think of this sequence as our highly deterministic tortoise. It makes slow, steady, division-free integer steps that perfectly and mathematically approximate complex irrational numbers, like 1 plus the square root of m. It provides absolute precision using only verified integer logic. No dartboard needed. And this brilliantly illustrates exactly what that looks like. Notice the pixelated lattice replacing the continuous curve. The Pell-Smith solution takes blurry, continuous Euclidean space and formalizes it into discrete algebraic steps. We are looking at a strict, pixelated rational lattice known as the symmetric diamond tile. It acts as a grid that perfectly replaces the continuous curve. You don't ever have to guess where a line is, because any integer solution corresponds to a perfect rotation. Section 5. Enter the ALU surveyor. So let's apply this mathematical breakthrough directly back to the microscopic silicon architecture. Because the math is now strictly integer-based, we can permanently kick out that chaotic FPU gambler and hand the logic over to our deterministic hero, the ALU surveyor. By applying this Pell-Smith logic, the system achieves what researchers call side-eye normalization. By anchoring the coordinate system to a constant where a equals exactly 1, we turn messy mathematical curves into straight, exact lines. From there, the ALU executes global remainder tracking. By explicitly tracking exact remainders in a deterministic loop, we get flawless single-entry bookkeeping. Basically, the ALU acts like a strict bouncer at the door. If the data doesn't perfectly align mathematically, it just violently rejects it. And the hardware efficiency of doing this? It is truly hard to overstate. The metabolic energy needed drops to a staggering 0.05 picojoules per operation. By anchoring to a discrete rational lattice rather than doing complex, lossy trigonometric scoring, that is an incredible 74 times reduction compared to standard 16-bit floating point methods. Absolutely massive. Which brings us to our final stop, Section 6, Absolute Digital Truth. So the crucial point is that we are witnessing a fundamental paradigm shift from spatial approximation to strict integer geometric rigor. In the old paradigm, the hardware relied on the FPU gambler, using approximate Euclidean maths, which gave us high energy use and constant non-deterministic drift. But this new paradigm, it relies on the ALU surveyor, powered by exact Pell-Smith mathematics, achieving a 0.05 picojoule energy footprint, and most importantly, absolute truth. By strictly verifying this integer logic, we bake an undeniable chain of title right into the silicon itself. The sources note that this actually restores Noether's theorem, a fundamental principle of physics, bringing true symmetry and reversibility back into our digital computing. It represents a massive, massive philosophical shift for computer science, and it's beautifully stated in this quote from the source documentation. We move from approximating a curve to possessing the state of the manifold. Really think about that for a second. The machine is no longer guessing where the data is. Because of exact integer identities, the machine mathematically definitively possesses its absolute state, without any of that lossy observer debt. And this leaves us with an incredible lingering question. If we can use this exact math to build perfectly deterministic digital universes, systems containing events spawned entirely without a predecessor, true orphans that can literally only exist at the dawn of time, does our own physical reality contain events that have absolutely no past? Take a moment to really think about that. Thank you so much for joining me on this explainer. Keep questioning the absolute limits of what we can compute, and I will catch you next time.